Hello? I'm just gonna be honest. I like making videos because for me, it's like a form of digitalizing my notes. And I like posting the things that I find cool that I want to make sure I don't forget. And I post the videos because if somebody else can learn from them, I think that's great. But always make sure to double check my work because I'm literally just some loser in my room. But it's like Winston Churchill said, a winner is just a loser who didn't give up. Anyway, let's talk about power series. So a power series, right? It's like a summation. It's like this, like, and I'm also not gonna edit this. Well, I mean, like, I'll edit it, but very lightly, because I spend a lot of time editing, and that's time that I could be doing math. So this is the general form of a power series, and um, and this is a coefficient here, and then A is where the series is centered at, graphically speaking. K is the power it's being raised to. Um, and x is the variable in question. So that this means the same thing as c sub 0 plus c sub 1 times x minus a plus c sub 2 times x minus a squared plus c sub 3 times x minus a raised to the third. And then this continues on, and let me see. We'll say mm, for c sub n, I think this is how it goes. I'm kind of trying to just do this impromptu here. For c sub n times x minus a raised to some power n, and that's where it stops. Okay, and this is a power series. This is a power series. Um, Now remember, a is what it's centered at, and a Maclaurin series is a well, maybe I should say that a power series is a way it's often used to try to approximate functions using quote unquote simpler functions, so to sort of like mimic it. Um, in a sense, it's for approximation. But a Maclaurin series, no, not McLaren, Maclaurin. A Maclaurin series, they will so this one has like a certain form of like, well, it's a summation. It's a summation of, well, we'll say k equals 0. So a summation from k equals 0 to infinity of c sub k times x raised to the power of k, and c sub k is just it's just some coefficient, right? And um, and because we'll say because the Maclaurin series, it's defined to always it's always at a equals 0. It's centered at 0. Well, that means that x minus a raised to the power of k equals um x minus 0 raised to the power of k, and that's going to equal x raised to the power of k. And a very famous Maclaurin series is e raised to the power of negative x equals the summation from k equals 0 to infinity of 1 negative 1 to the power of k over k factorial times x raised to the power of k. And and so the reason that I wanted to get into this today is because I learned something really, really cool how to do, and I just sort of wanted to like show you guys and just kind of talk about it a bit because I think it's actually really neat. Um so let's get started. This is sort of just a little bit of a predecessor. Okay, imagine that we have like some function f of x, and Well, I want to be more conservative with my space, so we'll work from left to right. F of x equals 5 times Euler's number raised to the power of negative x. And so imagine that we want to find the first few, or we'll say the first four non-zero terms of this series, of this Maclaurin series, um, for the given function. So we want to find the first four non-zero terms for this Maclaurin series, um, or excuse me. So we want to find the first four non-zero terms of the Maclaurin series for this function here, 5 times Euler's number raised to the power of negative x. Well, the function the function f has derivatives of all orders on an interval that's centered at 0, a equals 0, right? And so the Maclaurin series for f can be found with this formula or this theorem. F of x equals f of 0 plus f prime of 0. And well, it's going to be f prime of 0 times x degree 1 plus f double prime of 0 over 2 factorial times x raised to the power of 2 plus f triple prime of 0 over 3 factorial times x raised to the third. And then just note the orientation of this is the third derivative. We're multiplying to the x raised to the third degree, plus anything all the way up to um, the derivative of the nth order derivative of some function of that same function times 0 over n factorial times x raised to the power of n. And well, to determine we need to determine the first non-zero terms of this series. So we'll start by evaluating. Maybe I should box this up. To determine the first non-zero terms of the series, we want to start by evaluating like what's f of 0, right? Because we're going to find 1, 2, 3, 4. And well, oh, and maybe I should add that the approximation is going to get more accurate um as we start adding more non-zero terms, but we're going to go up to 4 here. So let's say we want to find f of 0. Well, we know that f of x is equal to 5 times Euler's number raised to the power of negative x. And so if we just plug in 0 for x, this is 0 by the way, that's going to be 5 times Euler's number raised to the power of negative 0, that's just going to be 5 because anything raised to the power of 0 is 1. And um, and so it's going to be 5 times 1, so we're going to have 5. So f of 0 is 5, so the first non-zero term of the Maclaurin series is 5. But then we have to determine the second non-zero term of the series, so that's going to require us to find the derivative of this function. So, um, so if we want to find f prime of x, well then uh, we're gonna have to take into account that f of x is equal to 5 times Euler's number raised to the power, or excuse me, f times Euler's number raised to the negative x power. And well, if you take the derivative of Euler's number, so basically like what we're gonna do is we're gonna factor out that 5, and then we're gonna take the derivative of Euler's number raised to the power of negative x. But when you take the derivative of Euler's number, see like it's just unbothered. Like the derivative of Euler's number raised to the power of x is just going to be Euler's number raised to the power of x, but this is Euler's number raised to the power of negative x. And when you have that, it's of the form um, e raised to the power of a times x, because that negative sign is technically it's -1. And so, and when you take the derivative of that, it's going to look like this. That a, it's going to come out front, a times Euler's number raised to the power of a times x. So for us, well, we're going to have 5 times the derivative of Euler's number raised to the power of -x, but that negative is going to come out front, so it's going to be negative Euler's number raised to the power of -x. And well, that's just going to be -5 times Euler's number raised to the power of -x. And so, um, right? I'm pretty sure. So then we have to find, well, we found f prime of x, so we want to find f prime of 0. We can get that by just plugging in 0 into our derivative here. So it'll be -5 times Euler's number raised to the power of -0. And, well, this is going to be -5. This is going to be -5. And so then we want to find the second non-zero term. So we want to find the second non-zero term for this, so we can plug it in, right? So the second um, non-zero term, well, that's going to require us to find the second derivative of our function here, f double prime of x. And we can look at the first derivative here. It is right here. And we're going to take the derivative of that. And so it's going to be, well, and we could just take this in our heads because, well, we're going to factor out that -5, and then we're going to take the derivative of e raised to the power of -x, and we already took the derivative of that. We know it's going to be -e raised to the power of -x, and so if you multiply -5 times -e raised to the power of -x, well, um, that's just going to be 5 times e raised to the power of -x, because those negative signs are going to cancel. So this is going to be 5 raised to the power, no, this is going to be 5 times e raised to the power of -x, I think. And then we're going to find the zero term, right? So it's going to be f double prime of 0. We'll go ahead and we'll plug in 0 into that. Um, I think, right? And so, well, that's just going to be 5. But we're going over 2 factorial here. We're going over 2 factorial here. And so and let's just do a quick review over factorials. Let's just do a quick review over factorials. So, um, let's see. 0 factorial is going to be 1. 1 factorial is going to be 1. 2 factorial is going to be 1 times 2, and that equals 2. 3 factorial is going to be 1 times 2 times 3, which is going to be 6. 4 factorial, even though we're not going up to 4 because that would be the fifth term technically here speaking, but if we did if we found 4 factorial, that's going to be 1 times 2 times 3 times 4, which is going to be 24. And then this is the same, like it's just going to keep going, right, following this trend. Um, Fun fact, factorials actually grow faster than exponents, which is really, really interesting and really cool. Um, but we'll just leave this here. We'll just leave this here, boxed it up, just so we can refer to it. Um, and so, where were we? So we want to find the zero. So this is going to be, we're going to have 5 over 2 factorials 2. So it's going to be 5 over 2 times x raised to the second power. You can't really simplify that. Well, technically we could, but I digress. So we found this is our third zero term, so we're going to find the fourth zero term. And so to do that, we're going to have we're going to need the third prime. And you could also write it with 3 um little commas here, but another way you could do it is like that. And it kind of looks like an exponent, but it's not an exponent. That's a 3, and that indicates that this is the third derivative. So we're going to do f triple prime of x, and we're going to take the derivative of this here. So let's take the derivative of that. Well, it's just going to be -5 Wait. Yeah, this is going to be -5 times Euler's number raised to the negative power of x. So let me just say -5 times Euler's number raised to the power of -x. And then if we want to find the if we want to find the 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 uh the non-zero term, well, that's going to be, hold on. Oh yeah. Okay. That's gonna be -5. So that's gonna be, so yeah, that's gonna be -5. But then we're gonna plug it into our function here, where we have, and we'll just go over here. This is gonna be -5 over 3 factorial, which is gonna be 6, and this is going to be times x raised to the third power. Sorry, I was just checking the work. And so the first non-zero terms of the Maclaurin series, they're gonna, well, it's gonna be, well, let's see, f of 0, which is gonna be 5. And then the second non-zero term is gonna be f prime of 0, which is going to be yeah, -5. No. Uh, oh, my bad. I'm so sorry, you guys. This is actually supposed to have an x right here, right? Because, yeah, we're supposed to plug that back into this. So f prime of x is, it's f prime of 0x, right? This is going to be -5 times Euler's number raised to the power of -0, right? And then, well, that's going to be, yeah, that's going to be -5x. And so then what we'll do is, so we're going to put an x, yeah, on that. And so this is going to be the second term of the Maclaurin series. And then the third term of the Maclaurin series is going to be right here, 5 over 2 times x raised to the power of 2, and then the fourth term is going to be -5 over 6 times x raised to the third power. And this is just the first part of the problem, and you might ask, like, Stella, like, what do you mean, like, you find this cool? Well, I find it cool because derivatives are cool, but here's where I really, really find it cool, all right? For me, one of the coolest things about mathematicians is their ability to just create formulas for things. Like, they like just sort of just create, like, look at something, see some patterns, and be like, here's a formula for that. That is the coolest thing I've ever seen in my life. Like, that, to be able to like have that ability is just, I just admire that so much. And so the second part of this problem here, which I may or may not have taken from my problem set, it says to write a power series using summation notation, and to find a pattern using the first four non-zero terms, which we've had the first four non-zero terms, and um and these terms, they're of the form, let's see, I do this, and these terms are of the form c sub k times x raised to the power of k. So c sub k times x raised to the power of k, oops, such that k is equal to 0, 1, 2, and so on. Wow, that ellipses looks so good. Anyway, so basically, c sub k is the coefficient of uh, x sub k. No, no, no. C sub k is the coefficient of x raised to the power of k. And so to do this, right, to create, we're going to want to use summation notation. So now we're going to introduce sigma into the into the problem here. And so, well, we have our first four terms. One, two, wait, no, 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 no. One, two, three, four. And like, we're just going to take inventory of what's happening, right? Let's take inventory of what's happening. So we can do this in blue. Our first, Sorry. I'm trying to think about how I want to put this. Our first term is 5. Our second term is negative 5x. Our third term is 5 over 2 times x squared. And then we have negative 5 over 6 times x raised to the third. And we're just gonna take inventory of the signs, like what's going on. Well, we see alternating signs, positive, negative, positive, negative. And this tells us that the pattern is always almost going to be um, negative 1 raised to the power of k. And that means that negative 1 raised to the power of k, it's gonna have presence in our summation. When we write this in summation notation, we know that there's gonna be negative 1 raised to the power of k present somewhere. So now let's look at let's just look at the magnitude, the size of the numbers. Let's look at the size of the numbers. We're gonna look at the size of the numbers and we're gonna ignore the signs, right? So we have 5, 5, 5 over 2, and 5 over 6. And then we're going to compare these to the factorials. We're gonna because the theorem has factorials in it. Um so we look at the original function right here and we say, well, there's a 5 in it. So we'll take 5 and we'll put it over 0 factorial, and that's going to be 5. And then we'll take 5 and we'll put it over 1 factorial, and let's see, that's going to be 5. And then we're going to take 5 over 2 factorial, and this is going to be 5 over 2. And then this is going to be, and then the next one is going to be 5 over 3 factorial, and that's going to be 5 over 6. So that means that there's this certain kind of pattern. There's a certain kind of pattern with these coefficients because we have our coefficient 5, okay, and then 5, well, that's going to be put over different factorials. Here it's being raised here, so right here, this is over factorial, 0 factorial. We just can't see it, so they don't write it into the theorem, but it's there. And then well, underneath here, this is going to have a 0 factorial in the denominator. You just can't see it because they're both 1, and there's a 1 over every number. I mean, excuse me, there's a 1 underneath every number. But so here's what's cool, right? Because right here, look, 5 over k factorial. So we can combine both of these patterns, right? There's a pattern here, there's a pattern here. We can combine these. These are components to create our summation. And so if I grab our c sub k here, that means that we're going to have 5 over, 5 times negative 1 raised to the power of k over k factorial. And then we'll put back that that um that x raised to the power of k. And well, a power series, let's see here. Power series, that's an R. A power series, well, the power series has a form of the summation of c sub k times x raised to the power of k, as we've established before. And we could put this into the power series form because we have we have our components here that we've identified, and we've written out our C sub k, and we're gonna actually, well, technically this should be here, but I know it's gonna be there, but so I put it there, but let me just write it out. From k equals 0, the summation from k equals 0 all the way up to infinity for C sub k, which honestly, let me just be real. This is the proper way to do it. C sub k equals 5 times -1 raised to the power of k over k factorial. And so we can write in our C sub k, which is 5 times -1 raised to the power of k over k factorial times k raised to the power, excuse me, x raised to the power of k. So the power series this is how you would write this as a power series. And I just think that's so cool because it's like we're going all the way up to infinity. This literally is just the coolest thing to me. Like you can plug in numbers for this and you can get a better and better approximation for this. And to me that's just like literally the coolest thing ever. Like I can't explain it. But then the third part of this question takes it a step further because the third part of this question, it's like we want to find out, like, does it converge? Does this go like no, 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 no. Um we want to find the interval of convergence, right? We want to find we want to find like for where if so if this converges, where does it converge? And for this, we're going to use something called the ratio test. Let me do this in like this kind of blue. Sorry, I want to see like I want to make sure this contrasts nicely, but I just want to well, the ratio test, let's go like this. The ratio test. The ratio test, it tests for convergence, and it says that if you have um if you have a series and you're looking at like the summation of the absolute value of a sub k, um well, if 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 r, let's see, if r equals the limit as k approaches infinity for a sub k plus 1 over a sub k, if this is less, if this quantity is less than 1, if this here is less than 1, if this value is less than 1, then the series converges. But if r, which is the same thing as this, as if the limit as k approaches infinity for a sub k plus 1 over a sub k is greater than, if it's greater than 1, it diverges. But if r equals, wow, wait, if r equals 1, if r equals 1, then it's inconclusive. Okay? So, I'm trying to like compartmentalize and figure out how I want to, how we're gonna do this. Let's see. Well, we need some room. We need some room. We need to find the ratio. We need to find the ratio r. And we know that the ratio, it's equal to the limit as k approaches infinity for the absolute value of a sub k plus 1 over a sub k. And well, let's just really quickly find like, and I just want to write this out. Um, like what's a sub k? Well, we have a sub k right here. A sub k is equal to 5 times negative 1 times, well, 5 times negative 1 raised to the power of k over k factorial times x raised to the power of k. But then that begs the question, what is a sub k plus 1? Well, to find a sub k plus 1, all you really have to do is just plug in k plus 1 everywhere where you see k. So, um, 5 times negative 1 raised to the power of k plus 1, right? Because there was originally a k there, but now we have k plus 1 over k plus 1 factorial times x raised to the power of k plus 1. So, well, we know what a sub k plus 1 is, and we know what a sub k is. So that would mean that we can find the ratio r equals the limit as k approaches infinity for a sub k. I just realized I'm probably going to need a little bit more room. Let's move this down. So the ratio equals the limit as k approaches infinity for the absolute value of a sub k plus 1. So on top here, and this is going to be a complex fraction, so we're going to on top here, we're going to have 5 times negative 1 raised to the power of k plus 1, and I'll stick that in the numerator. This x raised to the power of k plus 1 is going to go in the numerator. Because remember, there's just a negative 1 underneath it. And so this is going to be this quantity over k plus 1 factorial over, well, over a sub k. And so then that's going to be 5 times negative 1 raised to the power of k times x raised to the power of k over k factorial. And we're dealing with the absolute values here. And so then what we'll do is we'll reciprocate. So this is still going to be an absolute value, but it's going to be the absolute value of, ooh, I should be more conservative with the room because I know what's going to happen. At least I hope I know what's going to happen. 5 times negative 1 raised to the power of k plus 1 times k times x raised to the power of k plus 1 over k plus 1 factorial times k factorial over 5 times negative 1 raised to the power of k, that's a negative, raised to the power of k times x raised to the power of k. And, well, to solve this is going to require us, well, at least the way I would like to do it is I like to group things together so I can see what cancels. I generally find that to be like an easier way to sort of go about these things because there's lots of moving parts. So we're going to have 5 times negative 1 raised to the power of 1 raised to the power of k plus 1. And then I see like that this is also being raised to the power of k down here. And so, well, I'll just bring that 5 along with it, negative 1 raised to the power of k. And this is going to multiply to another fraction that we're going to separate it. And so I'll take this k factorial and I'll put it with this k plus 1 factorial. So we'll do k factorial over k plus 1 factorial. And then this will be multiplied to x being raised to the power of k. I should be more specific. So this is raised to the power of k too, but it's not a variable. It's not x being raised to the power of k. But now we have x being raised to the power of k in the numerator. We have x raised to the power of k plus 1. And then in the denominator, we have x raised to the power of k. So we'll find that these fives are going to cancel. These fives are going to cancel. Um, and then since those fives cancel, we're going to have negative 1 raised to the power of k plus 1 over negative 1 raised to the power of k, and we'll deal with that in a minute because we want to factor this k factorial fraction because k plus 1 factorial is the same thing as k factorial times k plus 1. These are the same. And we'll find that these k's are going to cancel, but we'll do that in a different color in a second because I just want to look at this here. So x raised to the power of k plus 1 over x raised to the power of k. Let me write out like a little formula really quickly. Let me try to like visualize this, what variables to use. Well, let's see. If you have like a fraction, x over x, and x, the numerator fraction x is raised to the power of m, and then the denominator is x is raised to the power of n, then you're gonna have x raised to the power of m minus n. And so that's what's going to be applied here. Box. And so basically what that means is that we're going to have times x raised to the power of k plus 1 minus k, because that's what this formula here says. That's one of the um, laws of exponents, I think it's called, laws of exponents. And oh yeah, dang, I should have did that while I had the purple out. I'm not editing this, you guys. Very light editing on this video. Um, because finals. But basically, uh, the same thing is going to be applied here, the loss of exponent. So negative 1 k plus raised to the power of k plus 1 minus k times, this is going to be 1 over k plus 1 times, well, that's just going to be x. Same thing with this is just going to be negative 1. So this is going to be, wait, yeah. So negative 1 times 1 over k plus 1 times x, which, well, this is going to be, uh, how do we want to do this? Negative, there's two different ways I could think to write this. Well, there's a few, more than two. There's a lot of ways we could write this, but we're going to go like this. Negative 1 over k plus 1 times x. But this is going to be the limit, right? Because we're trying to find the ratio. We're doing the ratio test. We have to address this. All right, so this is going to be the limit as k approaches infinity for the absolute value of negative 1 over k plus 1 times x. Oh, right, and this is equal to the ratio. Well, this is an absolute value, so we're going to do, and we honestly, that x doesn't depend on k, so we could just factor that out. X, the absolute value of x, times the limit of as k times the limit Uh, all right. The absolute value of x times the limit as k approaches infinity for one, and we could drop the absolute values because we're just gonna get rid of that negative. Um, yeah, drop the absolute value brackets. Um, the limit as k approaches infinity, the absolute value of x times the limit as k approaches infinity for 1 over k plus 1. And, uh, well, so let's think about this. Like, what happens as k approaches infinity? Well, as k approaches infinity, we're going to plug in larger and larger and larger values for k, and then that means that one's going to be getting divided by smaller, I mean, excuse me, one's going to get divided by bigger and bigger and bigger numbers, which is going to mean that it's going to become smaller and smaller and smaller. So essentially, this is basically, I mean, I have to be careful here, but one way you might want to think about this, or one way that you could think about this, or at least the way that I think about this, is 1 over infinity plus 1. Well, that's just going to be 0. So we're going to have the absolute value of x times 0, and that's going to be 0. And well, 0 is less than 1, so it converges. R equals 0. And R equals 0, well, that doesn't depend on x, and that means that R is less than 1 over the interval. So let's see here. R is less than 1 over the interval of negative infinity to infinity. And so I just think that's just so cool. Like I just love that kind of stuff. I really do. I really do. And I just love math and so yeah, that's pretty much it. So thank you guys for watching my video. I don't know if I'm gonna post this just as a video or if I'm gonna throw this in with a bunch of other um, videos that I have because I made a bunch of other videos that I haven't posted because I'm just avoiding editing because I'd rather do math than edit. But maybe I'll just post this. I don't know. We'll see. Thank you for watching. Have a good day.